Okay, hi everyone. Thank you for maybe not too loud. It's good. It's better. Yeah. Thank you for being here today with us. So we're going to talk about Talos and Omni, of course, and how we are using it at Ubisoft. And it works. So first, a little bit about us. We are Luis and Vincent. So here's Luis. I'm Vincent. Before I forget, if you have a question, anything, want to get in touch, we are here for the whole day. Otherwise, you can find us online on the Side Arrow community Slack, on GitHub, on Twitter, wherever you want. So we work at Ubisoft in the IT department. We work on an internal developer platform that provides managed services, such as a managed Kubernetes cluster. And maybe, Luis, you can explain to us why at Ubisoft we would want to create our own managed Kubernetes cluster instead of using one from the public cloud, for example?
Yes. First of all, is there anybody in the room that have already played some Ubisoft games? Yeah. So, okay, I don't have to explain a lot of this. We have a lot of really known brands like Assassin's Creed, Just Dance, Far Cry, or Rainbow Six Siege. So a lot of games means a lot of players and a lot of players playing online. So we have a lot of machines to manage in order to let people play some games. They are running. We are running game servers to let people meet online. They are mostly hosted. They were mostly hosted on Windows physical machines that were in 2 data centers, one in Paris and one in Montreal. The ones that are near our historic offices. But the problem was that we needed more point of presence to serve people from other parts of the world, like Asia or South America. So at the time, we went to virtual machines on public cloud and with the public cloud, we went to parts of the world that we couldn't access, and we had some OpenStack inside our data centers. From the issue was public costs mostly. It's really expensive to run some virtual machines on public cloud. So at the time, Ubisoft made the choice to acquire a company which is called i3d.net, which is specialized in data center hosting game servers and to run on new data centers, new games on Linux with still public and internal cloud, but having less issues with the cost. But there was still a problem with how we manage machine because we had a lot of different machines. So we turned after that to Kubernetes, really known, with Agones that we created with Google, and to public cloud, but once again, cloud costs. So now we are turning to hybrid Kubernetes clusters with our own machines inside i3D and our historical data centers, and to public clouds to have the flexibility and some features that we will talk later. So it's a perfect time for Talos and Omni that Vincent will talk about now.
Yes, just to make it clear, what we're trying to do right now with our new platform we are building. So it's still something that we are building right now. So we don't have games right now on Talos. It's our next generation platform. And what we are trying to do is to bring together public cloud and on-prem. So we're not trying to fight one with each other. And we'll go into more details later. So why Talos? So I think a lot of you already know Talos. So I won't go into too much detail right now, just highlight a few of the features we really like. So the first one is kubespan, because we said we want to have hybrid cluster. So that span across multiple provider, cloud provider, on-prem. So kubespan will allow us to have an internal mesh network inside our cluster. So that's really nice for us. It's secure and everything. API, of course, because we are developers. So we really like what we can develop against an API, build automation, have audit logs and things like that. It's so much better than having to run through SSH command and things like that, and parse the output. Immutable. So I think Steve did a good job of explaining why immutable is a good thing for an operating system. It's safe for us. And maybe the most one big important topic too is Kubernetes native. Talos does one thing, it does Kubernetes and only Kubernetes. And that's very important for us because we know where the focus is. So we can be assured that it will always stay focused on doing Kubernetes. So that was why we went with Talos. And we are also using Omni. So just to explain why we went with Omni, I'm going to take a step back and start at the beginning of the project. So a little bit more than a year ago, we said, okay, we're going to build a Kubernetes platform on top of Talos. So we want to create this hybrid Kubernetes cluster with part of the control plane on the public cloud, worker node in our own on-prem data center. And we're going to do everything ourselves because we are developers. We want to start from scratch, rebuild the world, and things like that. So we're going to write our own machine registry, which is basically what Omni does, part of it. So all our machine can connect to our registry. We'll be able to talk back to them, configure them to make them join cluster. That was our goal, and we had a lot of people interested in that use case at Ubisoft. So we started to have a lot of different use cases. One use case we started to work with, for example, is generative AI. I think a lot of people are interested in generative AI. It's a hot topic. So we have a lot of generative AI application at Ubisoft. Some, for example, to generate image, such as this one. So it's been generated on an application running on a serverless platform, running on Talos in one of our POC that we did with Talos. So we are trying to do a lot of different things. We are trying to talk to too many people to support too many use cases. So we quickly found out that it was not efficient. So a few months later, we decided to change our plans and to focus on a single use case, similar to what Talos is doing, only Kubernetes. So we selected a single use case, running game server with Agones. So Luis will explain in a few slides what is Agones and how it works and things like that. And games have a very particular release cycle. It takes a long time. And if you want to have them on your platform, you need to get them early on the platform while they are still on the development phase, because after that, it's too late. And once they are in the validation phase or live, so running, it's too late. They won't change platform. It's too risky and things like that. And they don't have the budget anymore because they are already developing the new game. We wanted to deliver our platform very fast to be able to attract games that are in development right now so that next year they can be live on our platform. And to do that, we say, okay, we can't build everything ourselves. We are going to have to build on top of something that exists, Omni. And building on top of Omni was really a game changer for us because it really allowed us to build much faster. So to give you an example, with Luis, we joined the project in December last year. And for March, we had an API running on top of Omni. So we didn't know neither Talos or Omni. And with 3 developers, 2.5, we built our API and everything on top of Omni, and we had operational cluster. We still had a lot of challenge to tackle after that. But very quickly, we could build something on top of Omni that was really a game changer for us. So this is why Omni. This is also generated on our generative AI application. And it doesn't work. It works. And Luis, maybe now we can talk about Agones.
Yes, no, we are a few slides later. So I'll talk about Agones now. So the promise of Agones is to run your game servers everywhere Kubernetes is running. You have to know that a game server pod is a custom resource on Kubernetes, but it's not like your regular your regular pod. It's not stateless, as you have some players that are initiating session on your game server, and you don't want them to be cut for their game, or they will be really angry about that. Agones will help you with that, with keeping your sessions alive, and to keep them on the same machine. Also, it's not plain HTTP protocol. It's a UDP with a proprietary protocol on top of that, running through a node port directly on the machines to avoid any latency, which is another thing that players are angry to. So the promise is to orchestrate game servers, to provide game sessions, but also to have metrics and monitorings to keep track of your servers. So we have inside Ubisoft a team that is taking care of that into an internal product with an operator with some SDK tooling and running that on the major cloud like AWS, GCP, and Azure, but also in our own data centers in Ubisoft and in i3d.net. So how are we using it with Talos? So we are trying to build some hybrid clusters with using the most of our options for both of them. So we are using the public cloud for the control plane and internal cloud, but mostly virtual machines because we have the flexibility of creating and deleting machines as we go. And we use features that we don't have actually with metal machines like load balancer and storage solely for Kubernetes. And for the workers, we are using game servers on premise because big machines with a lot of CPUs, a lot of RAM, like you can see. And we can group them by huge numbers like 32. And you have to know also that the connections are not using the control plane at all from the player point of view, but directly to the game server, which is really nice. You have big machines with almost no latency. And Vincent, you can tell us a bit more about how we are doing this?
Yes, so our product is basically an API that we can use to create and manage Kubernetes cluster. So we have a few core concepts because we are creating Kubernetes cluster. Of course, we know about cluster and node pools. So machine set in the Omni world for those of you using Omni. We also have the concept of templates because we are building a managed offering. We want to make it very simple for our user. Steve already said that Omni is meant to be simple. We found it a little bit too complex for our user to have to get into the details of machine and things like that. We'll see in the demo later, but you can basically say, I want this template of cluster with this template of node pool and so on, and compose your cluster like that. And it's very simple, so it's better for our user. Internally, how it works, we use temporal. So I don't know if some people know what temporal is or no, nobody. One, temporal is an open source workflow engine that you can use to execute workflow. So we have different kind of workflow. We have what we call short-lived workflow. So for example, when a user is going to talk to our API to create a cluster, we're going to, so it will be, it can take a few minutes, like 4 or 5 minutes to create a cluster. So we'll just answer right away that the cluster is being created and we'll perform all the operation asynchronously. And we are going to use a workflow so that we can decompose each step in different activities. And temporal will make sure to retry the different activities if it fails. For example, if we try to talk to Omni to create a Omni cluster resource and if it fails for some reason, network issue, Omni is down, no, it shouldn't happen, then temporal will retry that specific step and it won't try to redo everything before. So if we made some calculation of resource or things like that before, it won't redo everything. So we are using that for all our Omni interaction or third-party interaction. We are also, so once we have an Omni cluster ready, we are also deploying, we retrieve first the kubeconfig from Omni, and then we are connecting directly to the Kubernetes API to deploy what we call our application stack. So all the Kubernetes components that we want to make sure they are deployed to have a ready cluster, so CNI, such as Cilium, CCM, Cloud Component, Cloud Manager, and other components for the metrics, collection of metrics, of logs, of everything. And we are also doing validation of all these components that we are deploying. So we are deploying them in parallel, and for each sorry. We are running conformance tests. So we are reusing the Kubernetes end-to-end conformance test and selecting only specific use case to make sure that each component has been properly deployed and is working as expected. And once the cluster has been deployed, we start what we call long-lived workflow or daemon workflow that will have a lifetime of the cluster, the same lifetime of the cluster. For example, one we call the Sentinel workflow that will watch the status of the machine, of the resource in Omni, and make sure, for example, that if one machine goes down or lose the network connectivity, we can see it, detect it, and remove it from the cluster to replace it with another node. So I'm going to go into more details into that specific use case later. And we can also have another workflow that will automatically detect change in the Omni status for the different Omni resource, such as cluster, machine set, and things like that, and store updated status in our own API so that our user can know the real-time status of the resource without going to Omni, because that don't talk to Omni directly, only to us. If it's too much text, we'll do it like that. So it's a little sequence diagram of what happens when a user on the left tries to create a cluster. So as I said, it's talking to the API, which answer directly, and everything then is asynchronously. On temporal, we have a big workflow that's going to create the cluster in Omni, for example. So then Omni on its own is going to select the machine and to configure them so that they can join a cluster. We retrieve the kube config and we configure everything, and then we say, okay, it's ready, and we start our daemon workflow that will work for the life cycle of the cluster. So everything is good, it's easy. The only part we haven't talked about yet is how do we set up this machine, connect them, and that's for you, Luis.
Yes, so before provisioning machines, let's talk a bit of how we are retrieving Talos images. So we are using a really awesome tool that is provided by the Talos team, which is the Talos Image Factory. And it's available through REST API or on the internet. And you just have to specify some kernel arguments that you would need, system extension, or even custom image labels. And it will generate automatically a kind of hash, which is called a schematic ID, that will allow you to download the image that you need in several formats. So for the major cloud, for OpenStack, for anything, and just put it to create virtual machines or metal machines. For our use case, we have basically three kind of machines: the virtual machines, the internal meta machines, and the i3D .NET metal machines. The first one are the most easiest one to administrate. We are using mainly Azure and OpenStack, and we are provisioning the virtual machines through a Pulumi application written in Go. And we are directly using the Talos Image Factory through the REST API to download images corresponding to what we need and upload them to the corresponding cloud, so Azure or OpenStack, and generating the provisioning the virtual machines. After that, we have the internal metal machines located into that the Ubisoft data centers, the historical ones. And there is not a lot of tooling to manage them. So mostly everything is done by hand. So we have to do some digital rebars and scripts to manage them. We also had to use some custom Talos config to give them some IPs and to manage the network. And we also had to create our own service to manage their identity, their UID, and know which one corresponds to which one. And for the last type of machines, so the i3D.NET metal machines, it was really nice because I have a REST API to manage them that you can use through Postman, which is called the Flex Metal REST API. There is already a managed network, so no need to take care of the network. And there is, and it's interesting, a native integration with Talos Factory. So we just have to give them the schematics ID that we need, and they will automatically install the metal server for us at the versions that we need. So here's an example of a response from the Flex Metal API. So we can see at the top the version of N, also an example of schematic ID that we use to generate, to provision these metal machines. And now it's time for demo, I think.
Yes. Okay, so in this demo, I'm going to show you how we can create a Kubernetes cluster using our product, our API. And I'm going to show works under the hood. So I'm going to show you the UI of Temporal, so we can see the Omni UI and so on. Okay, it works. I need to pause at some point. So we're going to use our CLI. So our user uses the API, but we also have a small CLI that we can use. So here I'm just listing the different templates for the cluster. So where we can configure the number of control plane nodes. We have the same thing for the node pool. So we have the spec for the machine and so on. So it's very easy then to say, I'm going to create a cluster. I'm going to name it TalosCon. So yeah, sorry, no live demo because we weren't sure of the Wi-Fi, just recorded. We can give it a specific location and we can add node pools. So I'm going to create a cluster with 3 control plane nodes and 1 node pool with 1 node inside of it, which will be what we call a game server node that will be in i3D.NET data center. So we can see that we have default fields and settings for Kubernetes version and things like that. And I have an answer right away. And then if I go to the temporal UI, I can see all the workflow running. And I have one, for example, that is going to be responsible for the creation of the workflow. So the workflow ID is in the name of the workflow. So it's very easy, even if you have lots of workflow, to find the one you care about. And you can see all the input parameters and output parameters of your workflow, which is very interesting when you need to debug and understand what's happening. So we can see we have one node pool with one node inside of it. And we can see all the events or all the activities, everything that happens inside the workflow. We can also start a child workflow, such as this1, for example. And this workflow is responsible for the config patch. So I'm not sure if everybody is aware of what the config patch is. It's an element of configuration for Talos. And because we are using Omni, we need to send it to Omni, which will then send it to our Talos machine. Again, I can see the input and output of my workflow. I can see all the activities inside of it. And this one, for example, is going to synchronize the config patch with Omni. So if there is a network error, Omni is down or whatever, it's going to retry only that activity. So I can see again the input, just similar to function, but I can see the input and output of each one, which is again really good for debugging. And now we can switch to the Omni UI. Maybe some of you are already using Omni. We can see our cluster, and I'm going to select my cluster. We are also using annotation on the cluster to add more details, so that it's easier for us if we want to debug and to find which cluster with its human readable name and things like that. So I can see the node. So as I wanted, I have 3 nodes control plane and 1 worker node. So they are not ready yet because they are still being installed. You can see the Talos version and everything. I can see the config patch that I've been generating and sending to Omni, such as one, for example, to configure the firewall rules and things like that. And then at some point, okay. So now I can go back to my CLI and see the status of the cluster. So it's telling me that it's being created. So I can have more details in a human readable format or in JSON to see in which state it is. So it's still doing the validation. So if I go back to the workflow, I can see that now I have a lot more workflow running because when I'm installing what we call our application stack, so Cilium and things like that, I'm doing everything in parallel. So each one is a different workflow and we can run them in parallel. So now let's have a look at what is running inside our Kubernetes cluster that has just been created. So I'm going to retrieve the kube config from our CLI, but under it, it's going to talk to Omni. So I'm going to list all in the cluster. And I can see, for example, Cilium being installed. And at the same time, there is a conformance Cilium pod, which is a conformance test being executed. And we're going to have other conformance tests running for other components, such as I can see a CSI. So it's a component responsible for the storage part on Azure. So this cluster has a control plane in Azure, as you can see right now. So 3 nodes for the control plane. So I'm going to just pause it. Yeah, it's still running. Yep. So as you can see, we have the control plane, which is composed of node in Azure, and our worker node, which is on-prem. So now that should be ready. So everything has been installed. So I can make sure that my cluster is ready. It's going to tell me, yes, it's ready. Yes, it's ready. Perfect. I love it when I know the end of the movie. I'm going to ask Omni just to be sure, but of course it's going to tell me it's ready because that's where I got the initial status. And if I go back to my workflow, I can see that I have only 3 running workflow now. One, for example, is a Sentinel workflow that we start when we create the cluster and which is going to query Omni regularly to check the status of the machine. And what's interesting again is that I can see all the output directly. So I can see each machine with its output, is it ready or not? And then I can try to detect if we have a node that are if all the nodes are healthy or not. So that's it for the demo. Okay, I'm going to stay here. And I'm going to go into a bit more details into how we use Omni. We are writing Go applications, so we are using the Go client to connect to Omni through the official Go SDK. And we also use the OmniCTL CLI for scripting, debugging, things like that. So an interesting use case we have is that we want to automatically remove broken machine from our Omni cluster. That's something that Omni doesn't support out of the box. For example, if you have a machine that you plug the power off, for example, Omni won't do anything. So you will have just one less node in your cluster, but it won't be replaced, even if you have other available node available with the right label and everything. So what we do is that we run what we call the Sentinel workflow that I just showed in the demo. We try to detect faulty machines. So in a regular interval, we check the status of the machine. If we find that one is an LC, we're just going to remove the machine set node resource in Omni. So it's a resource that identifies a specific node in a node pool. And if we remove it from Omni, Omni will understand that we don't want to have this node in the cluster anymore. So it will connect to the Kubernetes cluster and remove the node from the kube API. And then it will remove the node, the machine from the cluster in Omni, which is pretty nice because then the machine will still be connected to Omni if it's still alive, but it has an issue, or if it's not alive. And then we can do whatever we want with it. So if it's a VM, for example, we can just delete it and recreate it. If it's a metal machine, we can add a specific label so that it won't be selected to join a new cluster later, and we can take it offline and inspect it. And the interesting part of it is that Omni is still going to add a new node to replace this one. So when you really remove the node from the cluster, Omni will detect that it has only, let's say, 2 nodes in the node pool and you want it free. So it's going to select an available machine and put it back in the cluster. So that's pretty nice. And another topic we had very early on when we started using Omni was monitoring. How can we know what's happening? And we wanted to know it like on our side, to have data and everything, historical data. So we quickly wrote a Prometheus exporter. I think that was our first experience with Omni SDK in Go before we integrated it in our product, in our API. So we retrieve the different, so we retrieve a few Omni resources, such as cluster status, machine status, the machine status link, which is a specific Omni resource that tells you when a machine last contacted Omni, so if it's alive or not, basically. And machine class, so if you're not familiar with Omni, a machine class is just a meta resource that will allow you to group machine by label. So when you are going to create a machine set in Omni, a node pool, you can say it's going to use machine from that machine class, which is just an indirection to say, I want to select machine with that specific label. So for example, it will be, I want a machine in an i3d.NET data center located in Paris, and we don't have zones. Or with specific CPU and RAM and things like that. So this is a Grafana dashboard. So we have available machine by provider, by machine class, by version of Omni. So when we upgrade of Talos, sorry. So when we upgrade Talos, we know that we didn't forget a machine with older version. So it will still work. That depends on the use case, but for most use case, it will be able to upgrade the version of Talos. But it's depending on the machine, it can take more time, which means it will take more time to create a cluster if it needs to upgrade the version of Talos on the machine first. So usually we try to force them when they are idle. That was how we use Omni. Now another topic is how we don't use Omni, or when we don't use Omni. Sometimes we need to bypass Omni, so we have a specific use case for that, is how we access the Kubernetes API. So when you use Omni, all your interaction with the Kubernetes API of your cluster will be through Omni. They will provide you with a load balancing and everything, feature to control the permission based on Omni user and things like that, or Omni service account. For our use case, we wanted to have a very fine-grained permission. So the team working on top of us that deploys Agones, their managed operator and everything, they have their own user also, and they want to control the permission with very fine-grained permission. And of course, they don't have Omni accounts, they don't know what Omni is, and they don't care. And as I explained, we can have a control plane with a multiple node, and this node can be taken out and replaced during the life cycle of the cluster. So what we did is we based our permission on Kubernetes service account, so it's easier for the team on top of us to create service account with specific role. They don't have to care with Omni. And then we needed to have a direct access to the Kubernetes API. So we just expose the Kubernetes API on the internet, and we set up a per cluster. So it was a very first easy solution. Maybe we'll have a more complex one later, but this is a first good. So one DNS entry per cluster with a record that's going to point to one of the control plane machine. And then we have a workflow, daemon workflow, that will just watch the status of the control plane machine and make sure that our A record always point to an LC control plane machine. So even if we remove the machine pointed to by the DNS, it will be replaced and it will always work. And because like most of the traffic to the Kubernetes API is from inside the cluster, it's not a big issue if we are using only one machine for our external point of entry to the Kubernetes API because it's for debugging or things like that. So that was one of our challenge, but we had a few more challenge, and I let Luis talk about our other challenges.
Yes, so the first change was some kind of mindset change. When you are a guy like me that is going to ready to install his preferred operating system, you just go to connect through SSH and do the rules for your firewall or anything by hand. But no, we can't really do that as everything is a resource, which is a really great thing. But it was a mindset to change, really. And there is a lot of resource, like you have machine status link, and even for the firewall rules, actually, you have to find which resource it is, which is good because it's relying on the API. But no, I can say, by the way, use Talos. We also had some metal machine management issues. As I told earlier, the ones that were located in the historical data center were a bit tricky, and we had to treat them individually, pets, in order for us to make them come back to the herd and let our colleagues just see them as cattle, or user actually, to see them as cattle and not be bothered with that. We also had to do some load tests that on did, and you can talk about it much better than me.
Yes, so as I said, we don't have real games on our platform yet. So before having any game, we first need to make sure that our platform will be ready for that. And the production team, the team that are responsible for developing the game server and for their operation, are really passionate about hardware. So they already benchmark the servers they are going to use when it's on public cloud or internal cloud or on-prem. And so we had to do a lot of load tests to make sure that our platform will behave the right way and everything. The load test we did is to start 5,000 game server, so basically 5,000 pods on our game server nodes. So in our base setup, the cluster is composed of around 30 nodes, game server nodes, so worker nodes on-prem. We started around 40,000 game sessions, so basically user connecting and doing something, which is generating a lot of CPU load and UDP traffic. It's an important component we wanted to test because I think it's the first time we are using Cilium for game server use case. We generated around 700 requests per second to the Kubernetes API internally. And we had a lot of different tweaks to do and to apply to the Cilium configuration, etcd configuration, and other Kubernetes component configuration to make it work as expected, so that then the production team will be happy with it and will be welcome to deploy that game on it. So as I said at the beginning, we were able to build an API very fast based on Omni and everything. And then we spent a lot of time working with or fighting with metal machine management, tweaking of configuration for the load test and everything. But now we are in a much better position. So what's next for us? First, new feature and load balancer on-prem. So we said we don't care about load balancing on-prem because the user will connect directly to the metal machine on a specific port. That's true for the game server, but to be able to provide to our users the best playing experience, we need to find the server that will be closest to them. So we have an internal set of tooling that will take care of that. So when you first connect to a game, you will do what we call a matchmaking. So we'll select the best server that we can connect you to. And we have on the server side a component called quality of service that is deployed as close as possible to the game server. And basically, your client will just send a series of ping requests to all the components in various data centers. So we need to host that component as close as possible to the game server, so that will be on-prem, and we need load balancing for that. So that's something we're working on, providing load balancing in i3d.net data center or other data center on top of Cilium. Louis talked about provisioning. Our current provisioning setup is out of bounds, so it's not very optimal, mainly in terms of cost. So we want to move to a more on-the-fly provisioning for our virtual machine to be more cost efficient. We know that it's something the Sidero team is working on in Omni. So we are happy to wait for them to build that so that we can build on top of their work. The same for the cluster autoscaler. For the moment, we really need cluster autoscaler in our use case because, in fact, a game will be deployed on a multiple cluster in different locations, and we can always autoscale on the public cloud. So we can live without it. But at some point, we know that we'll need to have a cluster autoscaling on-prem too, and that can scale dependently for different node pool. So for a node pool on-prem, for a node pool in the cloud too, because we have lots of different components. We don't have only the control plane in the cloud. We also have components such as Kubernetes operator for Agones and other components. And the last part, of course, we want games in our platform. So first, game in development, and then live games. So yeah, our initial challenge to have a hybrid Kubernetes cluster that could host game server. Basically, we've done it. We always have more things to do, but we are ready to host a game in development. That's it. Thank you. And I don't know if you have a few minutes for question, or otherwise you can. Sorry, 5 minutes. Yes, he's responsible for doing that.
Yeah, thanks. First of all, sorry. Yeah, first, thanks for this talk. Looks quite amazing. How many people are working on this abstraction layer on top of Omni? So it looks cool. It has a GUI, it has a CLI. How many of you guys are doing this?
3 developers and now 2. So we are 3 for a few months, and now we are 2 developers, and we had 1 SRE and now 2 SREs. So a small team. But all the Agones part on top of it is done by another team. So we are just providing Kubernetes clusters.
This is Ram. Thanks for the presentation. It was nice. I have 2 questions. Did you mention that you run your services on the node port? So I was wondering if you have explored, since you have a hybrid mode of cluster that operates between on-prem, OpenStack, and then Azure. So did you have a chance to explore open source load balancers like BlockCLB or Metal or anything similar? And why would you choose a node port over those load balancers? And another question would be, you mentioned for the most use cases, you did not have any issues during the upgrades for Talos. So I'm wondering if there is any specific use case that you found difficulty accessing the services, either during Kubernetes upgrade or Talos upgrades.
Okay. I'll start with the first question, load balancing. So what you need to know is that it doesn't need load balancing. So it's going to open the port to manage the port itself. So it has a specific notion of a game server inside of it, which is sitting on top of a pod, and each pod will open a port directly on the node in the range 7,000 to 8,000 by default. And basically what we're going to give to the client, to the user, playing on PC or outside console, is the IP of the machine on the port, and it will directly hit the pod. So we don't need load balancing and everything, just UDP traffic directly from one side to the other. For the new load balancer feature we want to have, we'll explore different solutions. So we're not there yet. For upgrades, we had a few issues with Talos upgrades, but it's related to our Metal machine. So everything in VM runs perfectly, no issue with, and so on. The issue we had with our Metal machine upgrading Talos is that we found out that due to the disk management issue, we had different spec of machine. We didn't expect that. Some of them with different setup of disk, and Talos didn't detect said the same disk. So I don't remember the flow exactly, but what happened is that it was not properly installed on disk, and so it wouldn't upgrade properly. So we had a lot of pains with that. So we were just trying to fix it at the root and to make sure that all machines had the same setup. But once done, it was easier. Basically, the issue we had is that if you don't install Talos on the OS, which can happen sometimes, or it was losing the disk. Anyway, it won't try to upgrade. So it said, I won't upgrade because I'm not installed. To upgrade from minor to minor. So for example, it was from 1.6 to 1.7. Other than that, for the moment, we've been doing like kind of top of the world upgrade for Talos. So when we upgrade it from 1.6 to 1.7, we just say, okay, we don't care about the running cluster and so on. We'll do it properly for the 1.7 to 1.8 upgrade. But because, again, we can upgrade the fleet of machine automatically. When we'll select a new machine to join new cluster, we can select a new version of Talos, new version of... I believe it should work properly, as it was working for the VM for the 1.6 to 1.7 upgrade. And Kubernetes upgrade, no issue. So, sorry. We don't upgrade live cluster that are running for this use case. It's not only for our platform, but also for Kubernetes cluster created on a public cloud. They never upgrade the cluster. They always create a new one and recreate everything and so on. Live upgrade of a cluster of Kubernetes, we don't care for the moment for this use case. But starting with different cluster with different version of Kubernetes, we didn't add any issue.